This is the basic setup of the famous Stern-Gerlach experiment. Silver atoms pass through a strongly inhomogeneous magnetic field. Its orientation is, for example, along the z-axis. Classically, we would expect an atom of silver to have a magnetic moment in different directions. It actually comes from the negative valence electron in the orbital 4s. If the magnetic moment is caused by a particle that is not spinning around itself, it will align itself parallel to the magnetic field. If a particle had a spinning motion of some kind, such as a top, its magnetic moment would maintain the angle between it and the field, and would perform a precession motion around the field lines. All that just means that in general we will get one line on the screen. But what we see if we actually do the experiment is that these atoms form two lines like this, which shows that, first, the particle, the valence electron in the atom, has some kind of spinning motion, as it is not completely aligned in the same direction with the field. And second, this spinning exists actually only in two states. It's clearly a quantized feature. The spin of each electron, or atom, can be either up or down. When we rotate the magnetic field, like aligning it along the x-axis, we still end up with just two basic states, right and left. It doesn't matter what angle we turn the device to, we always end up with two states. This measurement process is theoretically represented by the act of these spin operators. What do we do when we find new operators? One very important practice: we find the commutating relations between them. Do you see what we have here? The commutators are not zero. It means that there is an inherent uncertainty between these operators, between their different spaces. Suppose, for example, that we measure spin along the z-axis, we get the spin up and down. Immediately afterwards, we block those electrons with the down spin and let only those that have become in the up spin state pass. If we apply a magnetic field in the z direction again, we get all the particles with the spin up. This is not surprising since the first experiment made the spin state of these particles up, meaning it had prepared the up state. It also tells us that the upspin, or the downspin, is an eigenstate of S sub z. But now we're doing a third experiment, and letting these particles that all have spin up pass through a magnetic field orientated along the x-axis. The result is rather strange. We're going to get two types of particles, some with a right spin and some with a left spin. Well, it just seems that the new measurement doesn't really care about the old measurement along the z-axis. The two spin spaces are independent of each other. As you can see, we're filtering out the particles with right spin, and allowing only those with left spin to pass through a magnetic field in the z direction. Now this is really weird. Initially, we blocked particles with spin down after the first experiment. But in this recent experiment, we're seeing particles with both up and down spins again. It's important to note that the measuring along the x-axis has essentially reset the spin state along the z-axis. This clearly shows that there's an uncertainty relation among the different spin directions. We can only determine the spin states with respect to one of them. This is mathematically represented by the non-zero commutators between the operators S sub x and S sub z. And naturally, the same behavior applies to S sub y as well. Here's a simple homework. What would we get if we applied a magnetic field in the x direction to each of the last two states? The spin state of the electron before the measurement can always be written in terms of the eigenstates of one of these operators, but it is more common to use those of the S sub z, namely, up and down basis states. Let's say we have three people, A, B, and C. C has a pair of gloves. He puts each glove in a separate box, and gives one to A and the other to B. Then B goes on a long journey. Once there, he opens the box and finds the right-hand glove. At that moment, he realizes that the glove A has back home must be the left-hand one. Is this a big surprise? No, of course. The information in the gloves never changed during the journey. The right glove was with B and the left glove with A from the start, and have remained the same ever since. A very intuitive result. Now we replace the gloves with a pair of electrons. C prepares the two electrons in the state. The form of this state is really strange. Where is the first system and where is the second one? The first symbol in the ket is for system A, and the second is for system B. Without looking, C puts each electron in a box and gives a box to A and the other to B. They agree to measure, for example, along the same z-axis. Now B goes on the same journey, and upon arriving, he measures S sub z and gets spin up. B now knows this. If A measures S sub z too, he'll get spin down. Of course, if they choose to measure on two different directions, they won't be able to predict what the state of the other will be. Sometimes it is difficult to pinpoint the weirdness in this. The issue is quite similar to that of the gloves. Correct? Wrong. The problem lies in the state in which C prepared the two particles. Look here well, this state is called the state of maximum entanglement. We'll see why in a minute. In this state it is not known before measuring what the state of either electron is. It's either up, nor down. Only after measuring the same spin, S sub z, did electron A get a down state and the other an up state. In the classical gloves example, the information was already present before looking at the gloves. Also, does this mean that the information traveled faster than light, from A to B? Nope, of course. There was no information to convey originally because 1. A's electron wasn't either up nor down, and 2. The agreement between A and B that they'll be measuring only S sub z made the matter after measurement looks like the example of the gloves. If they use two different axes, such as S sub x and S sub z, they would have outcomes that are completely independent of each other. For example, B will get spin left, and A will get spin up. Neither will know anything about the outcome of the other. Now let's use the density matrix. I've made a separate video if you want to learn about it. The density matrix is generally given by. It is a statistical sum of the possible states of the system. First, what is the density matrix for this combination of states? We have to calculate the probabilities, right? The density matrix is given by. Notice, however, that our state here contains both systems in each term. The density matrix will be 4 by 4, and you can calculate it like this if you wish. Look how it's really that of a pure state. But we really don't even need to find it. It's enough to know the density matrix of one of the two subsystems. In official language we say, we don't need to know the degrees of freedom of the other subsystem. We have to find a reduced density matrix for one of the two systems. Say for B's electron. For this purpose we will sum over the possible states of A, we trace A out. In other words, each single term in the reduced density matrix of system B will be given by. Note that index A is the same everywhere. This is what we mean by summing over A's states. The Q's here are similar to alpha and beta from the previous example. The indices A and B can take both up and down states. Thus, we've reduced the density matrix from 4 by 4 to 2 by 2. There's a lot to learn from this little matrix. First, note that the diagonal elements are all 1/2. Recall that they represent the probability of different quantum states. Here it represents the probabilities of the spin states, up and down, of system B. The two probabilities are equal for both these basis states. Let's calculate the expectation value of the operator S sub z. It's 0. In other words, B has no knowledge whatsoever about the spin state before measuring. But the situation is even weirder if you remember that systems, A and B, are described together in the same state. It means that we know everything there is to know about the spin state of the total system, but we don't know anything about either subsystem. Wow, right? You know everything about your car, and nothing about each of its parts. Doesn't that make you wonder about the significance of the parts that make up the whole? Let's calculate the trace of the squared density matrix. If the trace of the square of the density matrix is less than 1, then it represents a mixed state. In other words, both subsystems exist each in a mixed state. Furthermore, the off-diagonal elements are all 0. It means that the total quantum system consists of two subsystems each with a totally mixed state. Similarly, a trace of 1/2 for the squared matrix means that system B is maximally entangled with system A. We can't know anything about either of the two subsystems before measurement, because they are both totally mixed. Furthermore, since the off-diagonal elements are 0, there is no type of coherent or interference within one single subsystem. In wave terms, a subsystem that is maximally entangled with another subsystem will not be able to form an interference pattern, as it has no coherence in it. This is entanglement. And here is the scale of its strength. Don't forget to follow the channel. Thanks for watching.